Okay, remember going back to the old. Okay, going back to the old Fermi idea of having a power law that's basically where the exponent is just the loss minus the loss rate versus the gain rate. And again, these are alphas.
How did you get it?
How did I get this?
No, how did you type it?
It's proportional to. Uh, Now let's go back to what we got from shock acceleration, and we see it's nothing other than that. Um, in other words, we had an equation, and we just equated uh, um, at the shock, we integrated over the shock, and we balanced this term with these two terms that were both together. They gave a delta function basically. And what this equation states is that this is a term that produces new particles at a given momentum p. Why does it produce new ones? Because it's in either direction when they cross the shock, uh, they gain energy relative to the local frame of reference. So, but because it had a negative slope, the gain is a fixed fraction of the velocity difference times that uh, negative derivative with respect to p. So this is just, if you have a distribution that's like this, and then you make a velocity transformation, so everything's now moving just slightly faster, then you produce this many new particles at a given momentum per unit time. You have a given number of crossings per unit time. And what does that balance? It balances this term. What is this term? It's the downstream velocity times the density, which is constant. Everywhere between 0 and plus infinity, it takes on the same value, which is why I call it f plus infinity. And this is just the rate at which particles are being convected to downstream infinity, namely to positive infinity. Plus is downstream, yeah. In other words, the density, shocks are drawn like this. The density looks like this, and the velocity looks like this. Sorry, it would be u, since it's the fluid velocity. This is density. So this is the shock. This is x equals 0, and this is plus, going towards plus infinity. So the rate of convection is u plus sorry, this is u minus up here. This is rho plus and rho minus. You know what? They have drawing in red. For once, I'm going to use the red. Okay. So the rate at which I'm losing particles by convecting them away from the shock, this is the number I'm losing per unit area, per unit time, um, is equal to the rate at which I'm producing new ones due, due to this uh, due to the fact that whenever they cross the shock, they're always accelerated relative to the local frame.
Well, physically, it doesn't mean if they're convected away, then the less chance they will cross again and again and gain more and more energy.
What?
If the convection is faster, that means the chances that they will cross shock multiple times goes down.
Right. But on the other hand, the amount they gain goes up.
In each crossing.
Because the amount they gain in each crossing just is proportional to the velocity difference.
In each crossing.
And the rate at which they're lost behind the shock depends only on
Downstream.
the downstream velocity. So that's why you have downstream velocity in one in the numerator, and then the 1/3 velocity difference in the denominator. So really, this is the power law is just the loss rate, which is proportional to U plus, times the gain rate, which is proportional to delta U over 3. So alpha loss is proportional to U plus alpha gain is proportional to U plus well, let's say U minus U plus over 3. So it's exactly what Fermi originally proposed, but here the escape rate is not free, and that's why it works. That's why people finally accepted it.
Basically, why each time that they cross the shock?
Why what?
Why each time that they cross the shock they gain energy?
Relative to the local frame. Because in order to cross the shock backwards, you had to be moving backwards. Velocity. That means since the velocity upstream of the shock is positive and your velocity is negative, then the relative velocity is enhanced in the new neighborhood relative to the old neighborhood. Now, what if you're going in the other direction? Well, if you're going in the other direction, then your velocity is positive, but you moved into something with less positive velocity. So once again, you're moving faster than the locals compared to what you were in your old neighborhood.
Oh, yeah.
So either way, either direction, it's always positive.
I'm sorry. From the upstream to the downstream, I understand. From the downstream to the upstream, the first one that you did, I don't understand.
That's the same thing because you're moving backwards.
Yeah.
In order to cross backwards, you had to have a negative velocity. But suddenly you find yourself moving in a relative to a background that has a higher positive velocity than before.
Yeah.
So your velocity difference relative to the background is enhanced in that direction too.
Yeah.
And you see, whenever you have compression, that's the way it always works. The walls, and if you're trapped between two walls,
Walls of what?
of cement,
No, I mean.
and they're approaching each other, and you're a ping pong ball bouncing back and forth, you'll always gain energy.
Oh, I understand, and I remember the math illustration that you did to the ping pong balls.
With ping pong balls,
but
yeah.
what are the walls?
See, in Fermi's original idea, he just said, let's say you have two magnetized clouds that they're approaching each other.
Okay.
But that was like totally off the wall. No, if you pardon the expression. Uh, uh, but here, it's the wall. One side of the shock is one wall. It's a thick wall.
Yeah.
It's infinitely thick, a half infinitely thick, and the other wall is the other side of the shock. It's also half infinitely thick. Anywhere it scatters, anywhere in this wall, is okay, as long as it. And the shock, which is infinitesimal thickness, is the space between the walls. So instead of having two infinitely thin walls and a thick space between them, you have an infinitely thin space and two thick walls. But the point is, from the point of view of the particles, they're converging because one is moving faster than the other.
Okay,
And it's really kind of neat. When you think of when Fermi had the abstract idea first, and it just didn't work. I mean, physically it was silly, even though it's the first thing you'd think of. It just didn't. It was too mundane. It didn't work. But shocks are precisely what he was looking for, and if he would have thought about shocks, he probably could have done the whole thing. But he didn't. He was a particle physicist. He didn't know it. He didn't think in terms of hydrodynamics.
what do you mean you didn't think of the shock, but it's not in the shock? The whole
What?
process is not in
The
the
whole
shock.
process is exactly in the shock. That's the one thing I ain't talking about nothing but
Yeah,
here.
so why he didn't think of shocks
Because he just didn't.
he did it
He said
regarding
he
something
said
else.
suppose I had a magnetic field line and I had one cloud moving in this direction and another cloud moving and the particles trapped between two clouds, and why wouldn't they go around the clouds? Well, maybe because they're trapped on the magnetic field line in between. And people tried to make things like this work.
Yeah, magnetically connected.
And people thought about that too, but not in the context of Fermi acceleration. The main problem was that the larger the gyro radius, the faster it would escape. You needed to have something where the escape rate had nothing to do with energy, and that's very hard in astrophysics. And the way it works here is simply because the shock is so large compared to the gyro radius that it's a scale-free problem. And anytime you have scale-free problems, you tend to get power laws. Because a power law is the one thing where the shape of the spectrum, it's the one spectral form where you cannot tell where you're at by the shape of the spectrum. Because there's no scale. Probably the first derivative with respect to energy is always proportional to 1 over e times some constant. But if you compare dDE to 1 over e, you can't use that to figure out what the energy is. If you have a thermal spectrum, it's an exponential. It's E over something else that has dimensions of E. So there's a characteristic energy in the problem. And any function of a dimensionless argument, like e to the x or sine x, cosine, if one variable is a spatial variable or an energy variable, then it has to be divided by some constant with the same dimensionality. But when you have a power law, um, you know, certainly if you have something that's a power law, it's, you know, x to the minus 2.7, then it's going to have to be e over e naught to the minus 2.7, because, you know, you need something dimensionless. But the point is, there's no way to pick this e naught, because I could pick it however I want and then simply renormalize the coefficient outside. So power law really doesn't have any energy scale in it. And in order to get power laws, you always look for things with scaling symmetry. Now, this is all up until now the linear approximation, the linear test particle treatment. You assume you had a shock profile, and then just calculated the response of test particles. In reality, if you have enough cosmic ray pressure building up, it will affect the flow coming into the shock. In other words, we assumed that U minus was constant until we got to the shock, and then suddenly it dropped. But what about the cosmic ray pressure itself? That should, if it's large enough, it should slow the fluid coming into the shock. And it's no longer correct to assume that U minus is constant all the way until the shock. A little confused.
Yeah, but can you
Look, you know that momentum flow is p plus rho u squared, right?
Right.
And p is equal to p gas, which is proportional to well, tell you what, let me just write it this way. P gas is equal to k times rho to the gamma, right? And P is equal to P gas, but it's also equal to the cosmic ray pressure, right? It makes a contribution. And what's the cosmic ray pressure? Well, it depends how many cosmic rays there are. Now, nothing in here told you how many cosmic rays there are. It's a linear equation. You can put as many as you want in.
How would you deal with it?
The way you deal with it, Well, first of all, what question do we want to ask? We want to ask, how much can you accommodate? Obviously, if you had so many cosmic rays that the amount of cosmic ray pressure was greater than rho u squared, there's no way this could be constant, because rho u squared can never be less than 0. So you can no longer say that u is constant upstream. If u is not constant, this is not quite right, at least over the scale that u is varying. And what scale is that? Well, it turns out that varies over all scales. And now suppose I wanted to ask how many cosmic rays do I get from a real shock? It's a legitimate question, and it's an important question, but you have to calculate it. And so far, we don't have anything that enables us to calculate it. And actually, this is a calculation that I did in 1979, and it's probably the thing I'm best known for, because it came shortly after the linear work, and it was all the rage at the time, and it also addressed another question, what even determines how many cosmic rays I get? And where did they come from originally? Why do some particles become cosmic rays and others don't? And is the composition of cosmic rays the same as the gas from which it came, or maybe some ion species
it has not
satisfy the selection criterion better than others. So you needed a theory for injection and for maximal pressure. And here's the thing: if you inject too many, and you end up getting more pressure than you're allowed, what do? You have to. The point is, you have to consider both problems together. And what I proposed is that it was the limitation on the total pressure that acted as a selection criterion for the particles to be injected.
okay.
And to see how that works, what I did is I said, look, let's say they're all injected. You can't, 100%, which is obviously too much, because you can't accelerate. You don't have enough energy if you're starting with thermal particles. If you're starting with particles and there's only, 1 keV for energy per particle, obviously you can't get them all to a GeV. And so obviously you have to select a small number. But my approach was to say, okay, let's say you don't. Let's say you select too many. What happens? And the idea is to solve these equations well, let's go back to the equation. It's to solve this equation, but with u selected so that the momentum flow is dictated by P gas plus P cosmic ray plus rho u squared is equal to rho u minus squared. In other words, the total momentum flux is a constant, and it's this, assuming there's no pressure at minus infinity. And here, but I mean, what I mean by u minus is rho of u minus infinity squared. It's also rho of minus infinity. And I can, since rho u is a constant, I can write this as rho u minus times u minus infinity. In other words, rho u minus is just a constant in and of itself. It's the mass flux, and that's non-negotiable. So really, uh, so if I can rewrite this where I have a clean space, like over here, this implies that P gas plus PCR plus rho u minus, this is a constant, times u is equal to that same constant times u of minus infinity. Oh, done. Alright, let me just write it like that. So that means that u is equal to 1 over rho u times times u of minus infinity minus p cr minus p gas. What?
Here.
In here, in here.
P gas, PCR.
Here, let's just write it this way. Rho u, and we'll write the rho u here. And then we'll just divide like that. How's that? Goddamn fucking self-perpetuator.
You still take it left.
Okay. So, now what's P cosmic ray? Well, P cosmic ray is just the integral the infinity of f of p dp. And if I write capital F here, if I write capital F, then I think this was d log p. And here I have to write the pressure per particle. Pressure per particle is px v, right? Alright, so you can write what u is in terms of an integral of fp. And how do you know what f of p is? Well, you use
We don't know what f is.
well, you have an equation. In principle, you have an equation to calculate it, because you had this equation to calculate f of p if you know u, and you have this equation. You have this equation to calculate u if you know f of p. So you have enough equations. It's just it's just they're highly nonlinear and multidimensional and integral, and
Everything. Piece of cake.
but if you use the right approximation, you can actually get an analytic solution. And back in those days, I certainly didn't didn't want to do a numerical solution.
What are the approximations?
What?
What are the approximations?
Well, there's this one, and it's a valid assumption. Assume that at a given p, this is small p for momentum, and this is small p for momentum. Rahul, you still didn't.
Yeah, I sent to our party last week.
But you didn't send it to me.
I
I'd
will
like
send
a
to
copy.
you. I forwarded him the emails I sent to you the last time.
You what?
I found backups in the emails I sent to you. You was
Okay,
sending a text file.
Please
I'll
send me
forward you then.
today. I
Okay.
want to see it
Okay.
because I want to see if I've been working on the latest version. How does the latest version compare to the one I'm working on?
This one I didn't correct. First memories.
Right. That doesn't answer the question quite, but all right. So let's suppose that at any given momentum, all right, it's going to be a while here. All right, I'm going to have to. I want to draw another picture to explain this approximation better. Suppose the shock is here. And suppose I'm upstream here somewhere. So what's the pressure here? Well, I know that the density, since I've solved this equation, since I know it decreases exponentially as x goes to minus infinity, I know that upstream of the shock, at different energies, they're decreasing at different. It's all exponential, but the length, the e-folding length over which the density decreases depends on the energy. Because particles with small energy have small diffusion coefficients, and this function e to the at x less than 0, this is f is proportional to e to the minus u absolute value of xd, because x is negative, right? So the smaller d is, the faster it dies. So this is for small d, and this is for large d. Now I assume that the diffusion coefficient increases healthily with energy. And realistically speaking, the diffusion coefficient should be proportional to energy. And remember, there's a huge range of energies here, because we're talking about 10 orders of magnitude in energy, because the gyro radius at low energies is so small, you could accelerate them, say, from below a GeV to 10 to the 15th GeV, 10 to the 15th eV, fairly easily. And they'd still see the shock as being infinite. So the idea is that the diffusion coefficient can change by a lot, whereas the pressure doesn't change very much as a function of momentum, or as a function of energy. So the idea is that if I'm at a point here, I discount all the particles at energies, like let's say I'm at this point here, and I want to plot f as a function of momentum. F is a function of momentum. So let's say at a given momentum, all particles at low momentum have basically not contributing. So we just count them to be zero. And all particles at higher momentum have their value, let's say, not much different from what it was at the shock. So here it's just a power law. Now I don't know what this power law is yet, because I don't know what this velocity is here. But for the velocity that I used for the upstream fluid, that I still have to calculate. But how do I calculate? I calculate by knowing the pressure. And to calculate the pressure, I simply, instead of taking F to be something like this, I simply take it to be a theta function times the value at the shock. And this P is determined by the condition that d of P over U is roughly equal to the absolute value of X, where X is the difference between the shock and the point upstream. Downstream, everything is still constant. That's okay. So G of P prime is the value of F P prime at the shock, and this is P prime, and I just integrate from P to infinity. That's the pressure felt by, P is the momentum of a given particle. And if I ask what's the upstream pressure, that determines the upstream velocity that I should use to figure out the spectrum for particles at momentum P, then this presumably is pressure, partial pressure. know, this is pretty damn useless. Oh, I'm sorry. You know, this totally cuts off here. This is just totally worthless. Uh, I think I'm just going to refer you to. The two papers, 1984 and 85, that probably do it formally the best. If you ever need to know this. Normally I don't go through the whole calculation when I teach the course, and which is why the notes are in such bad shape. I never actually do it.
The acceleration, we didn't do it in 87 with the blunt?
No, that was just a review paper.
Can I ask one more question?
Yeah.
So, what are the conditions in shocks in order to have a firm acceleration? Not all shocks have firm acceleration.
Yeah.
What?
Actually, they do.
Oh,
All collisionless shocks.
yeah.
In astrophysics, you seldom see a collisionless shock that doesn't produce high energy particles. The Earth's bow shock, to the max. I mean, it produces as many as the nonlinear theory predicts. The solar wind termination shock also produces as many as the theory predicts. Daniel Arad did his master's thesis on that, and it's not a strong shock because it's not totally collisionless. They're ion neutral damping, and the mean free path for the ion neutral charge exchange, it's charge exchange, which is like a collision. Um, the mean free path for that is actually comparable to the gyro radius of the cosmic rays, so it's the diffusion, like, so it's not a completely collisionless shock, but you do see a collisionless subshock, and its compression ratio is exactly what the nonlinear theory predicts. It predicts that the shock should be weakened by the cosmic ray pressure from a compression ratio of 4, which is what we got for a strong classical shock, to 2.5. And in the solar wind termination shock, the cosmic ray pressure slows the solar wind from about 400 to 300 kilometers per second. It's a combination of cosmic ray pressure and friction between the ions and the neutrals, because there are neutral particles coming in from the interstellar medium, neutral hydrogen, which is charge exchanging with the solar wind. But when it's about down to about 300, when it flows into the termination shock, and then downstream it's 120, which is exactly a compression ratio of 2.5. And uh, and everywhere else, I mean, solar flares, you get cosmic rays when you have shocks, and in supernova, individual supernova remnants, you see individual populations of cosmic rays that are made by that supernova. And in extragalactic nuclei, shocks from jets, you always see synchrotron radiation. Uh, so I mean, I don't think there's a single strong collisionless shock in nature that doesn't produce shock accelerated particles.
And why shocks with collisions don't produce accelerated particles?
Because they would lose their energy
Collisions?
with collisions. Um, anyway, this should be a capital P. Anyway, the physical idea is that the lower the energy of the particle, the, the lower the energy particle, the smaller the upstream velocity that it feels. These high energy particles feel like a compression ratio of 4, let's say. And actually it's more than 4 once you take the cosmic ray pressure into account. But let's say it's 4. But as it flows in, it gets slowed down. But which particles slow it down? It's the ones that get furthest upstream that slow it down first. And then as it gets closer to the shock, then it feels particles of lower energy, which don't get as far upstream. And the closer it gets to the shock, the stronger the pressure, because the more particles are included. You know, if you're way out here, there's less particle pressure, and as you get closer to the shock, this cutoff goes lower, so you end up having more and more pressure closer to the shock. And therefore the velocity difference that the particles feel goes down. So when you calculate the slope, since this is a negative number, the closer the upstream velocity is to the downstream, the smaller this denominator and the steeper the spectrum. So now, if I plotted the spectrum of particles, and let's say I do let me write in an expression for pressure, fully relativistic expression for pressure. It's the integral of px. This p here is momentum. Times Vx and I'll write it in terms of the original phase space density, which is little f of p times dqp. This is the expression for pressure, right? Everybody agree? This is the number of particles. This is the momentum flux in particles of velocity, of momentum p. How do I write velocity? It's px. It's the momentum divided by gamma, right? And this is what's gamma? Gamma is the square root of 1 plus p squared. Well, not 1, but m squared c squared plus p squared over mc squared. So that's the expression for pressure. And if I just replace x with x plus, I would simply substitute this in the approximation. I would substitute this lower boundary of 0 for I would include only the particles that were energetic enough to get that far upstream, but then I would use their value downstream. And it's a very good approximation. I mean, it's been checked against numerical calculations, and it's just fine. So So anyway, I think what I meant to say here is that the pressure felt by particles of momentum p is equal to the integral from p to infinity of the post-shock partial pressures in momentum p. And I think if you're interested, you should just check out these papers. There's also an easier version in 1979. But the one in 84 is actually somewhat more rigorous and correct. Um, okay, so that's all I want to say about shock acceleration. I mean, there's a lot of work that's been done on it. Finite shocks, relativistic shocks, and it's still not finished. Um, Anybody want a break?
Yeah,
Okay.
it is just transformations of energy, and the crucial part is that assumed in the frame of the wall is momentum is reversed.
The X moment.
Yeah.
Okay. What was the question? Just
Delta
about
E
the.
over E in relativistic
Oh,
case.
okay. Very good. Mm.
Because when there's only one thing, they think maybe this one fell off, but it was only with this one. Actually, some people ask me, where's the other one? I said, no, this is the style. You don't know? I'm so foolish.
Alright, I don't have enough room here to fill in the differences, but this isn't so bad, actually. G of P prime is just the partial pressure in P prime, and to state what is more explicitly, G in terms of F is just P. the square of the momentum in any one direction divided by gamma times f of p. That's what g is. It's partial pressure per unit momentum, and it's because each particle contributes this in terms of momentum transfer, rate of momentum transfer. Now I have no room here to do it here, but I did it down here. Suppose you computed the pressure in cosmic rays given the phase space density. And here, phase space density, I'm integrating over dqp to get pressure, which is 4 pi p squared dp. Now, what is F? Suppose F is a power in P. What power did we get for a strong shock?
Wait, but you have d cosine theta.
For a strong shock, it was something like df dp. I think it was 3. Well, df dp, which is dp cubed f dp, was equal to 3 u plus over u plus minus u minus, which is equal to minus 1 when u minus equals 4u plus. This is for classical shock. A strong shock, they just assume the compression ratio of 4 in the test particle theory.
You should have a 2 pi, not a 4 pi.
Here it's 4 pi.
D3p is 2 pi d cosine theta, not 4 pi, because in here you integrate from minus 1 to 1. If you
Yeah, okay. Here it's 2 pi, but here it's 4 pi.
Why?
It's still 2 pi here, right?
Why is 2 pi?
Because I'm still integrating cosine theta. Once I integrate from minus 1 to 1, that gives me another factor of 2. But you're right, here it's 2 pi. So that means the df let's say d log p. I think that's what this was. That's equal. So d little f d log should be minus 4, right? Yeah, because p cubed times, if this is p to the minus 1, yeah, if f goes as p to the minus 1, then little f goes as big F over p cubed. F equals big F over p cubed.
But why with the minus sign?
Because u minus is less than u plus.
It's opposite.
Okay, yeah. So if I use this, if f was p to the minus 4, then what would this integral be? P here is in units of m squared c squared. Which is why I'm just putting a 1 here. Sorry, in units of MC. Well, if P is greater than 1, which means I'm dealing with relativistic particles, then this is 1 over P, and this Fp to the fourth is just a constant, so I get P dP over P, which means I have a logarithmic divergence, which means there's an equal amount of partial pressure in each logarithmic interval. It means, G particles at 1,000,000 GeV or PeV contribute the same amount of pressure as particles at a GeV and particles at a TeV. It's just, in every decade it's the same. But in the non-relativistic limit, when P is much smaller than 1, then it's divergent. So if you plotted partial pressure, which I call G, as a function of P, it would rise linearly with P until you got to to the relativistic momentum, and then it would be level. It would just be a logarithmic divergence. And by the way, this logarithmic divergence means that the cosmic ray pressure is going to get very large, which means this can't be the whole story. But once you put in the fact that the spectrum steepens at low energy, and you put in the fact that there's going to be a maximum energy at some point, then it's going to always be getting steeper, because the lower the energy, the lower the velocity difference, and therefore the steeper the spectrum. Wait a minute, I stopped this at MC. So the partial pressure is well, the slope is always decreasing. Sorry, the slope is always increasing with P, which means it's decreasing as you go to low energy. Except that at MC, it suddenly, what was decreasing starts to increase again, and then again it has to constantly get steeper and steeper. So you end up with something like this. And by the way, this can turn up. This can go up as long as it's in any given regime, it's constantly increasing, and there has to be this break at when you go from relativistic to non-relativistic. So the nonlinear theory predicts and since this steepens very rapidly here, and this is many decades in energy, then for many decades it's actually flat. And it means that the viscous subshock has to produce a compression ratio that would give you something flat in the non-relativistic regime. And if you plug it into here to see what value of f, what value of df d log p you need to get something that's flat in the non-relativistic regime, it ends up being that u minus minus u plus over u minus over u plus is equal to 2.5. So that's where the prediction comes in, that the compression ratio of the subshock is 2.5. In other words, the shock just has to get weakened by the cosmic rays until they feed back in such a way as to get a nonlinear solution. That and the amplitude, the amount of area under this curve is obviously constrained by the nonlinearity. So it predicts exactly how much cosmic ray pressure you should get. The amplitude is the amplitude is predicted in units of rho minus u minus squared. That's obviously the total area has to be less than 1 in these units. Has to be less than, the total pressure has to be less than rho minus u minus squared. And everything else is determined by the solution to the equation and the boundary conditions and maximum energy and so forth. Alright, that's all I wanted to say about that. And this is, tomorrow's the last day, right? Okay. I think the one thing more I wanted to talk about in the course is second order Fermi acceleration. It's not so much important for cosmic rays, it's important for Comptonization of photons. A photon bouncing off a hot electron is just what Fermi proposed. It's like a cosmic ray bouncing off a cloud. It's a relativistic particle bouncing off a heavier non-relativistic particle. And it obeys what's called the Fokker-Planck equation. That's this. And basically it's a diffusion equation. But this is the diffusion term, but in addition to the diffusion term, there's also a systematic term. This just describes, if you just had this first term on the right-hand side, it would be a first-ordered partial differential equation, which you could solve by characteristics. And A is just the acceleration rate, the rate of gain of energy per unit time, dE dt for an individual particle. And if you ignored this second term, unfortunately I can't cover it up with my hand like it used to be able to do. But if you just solve dN dt equals minus dd of an, you'd solve it by the method of characteristics, and you'd show that everything just moves up in energy at a rate of a. The velocity, so to speak, in energy space, which is dE dt, would just be a. And you can also think of it, well, think of a packet moving to the right. And if you're standing at one point, the rate of change of the function is just the spatial derivative times the velocity at which it moves. So, you just look at this, at my finger here, you see that the function goes down as my arm moves. And this, if I ignore this term, this would just be time-dependent diffusion equation, where d is the diffusion rate in energy space. Now, suppose I had particles bouncing off, or relativistic photons bouncing off infinitely massive scatterers, so that I could neglect the recoil. And that's what happens That's what happens, let's say when you have Thomson scattering, when the energy of the photon is much less than mc squared of the electron. The photon basically conserves energy in Thomson scattering. And if it bounces off in the direction that the electron was moving, makes a head-on collision, then it's like hitting a tennis racket. It leaves with more energy than it came in the lab frame. And if it overtakes it, then it leaves with less energy. So that creates a diffusion coefficient in energy space. But there's also a systematic gain, because it's more likely to make a head-on collision than an overtaking collision, because the relative velocity is higher. Like you're more likely to have mosquitoes splatting on your front windshield than your back windshield. But the ratio of DNA is not free. It's determined by thermodynamics, actually. And the way to see that is to say, look, if the particles are infinitely massive, the scatterers are infinitely massive, then it's like they have an infinite temperature. They essentially have an infinite amount of energy. And you know that a lighter fluid and a heavy fluid, when they're interacting, would eventually come into thermodynamic equilibrium. But in this case, thermodynamic equilibrium is that the light particles are equally distributed in phase space but correspond to an infinite temperature. That's the steady state solution. So phase space is populated uniformly in energy. And if I make these are all supposed to be small n's, and these are all supposed to be small p's. If n is it's also a function of x in principle, but let's say that it's constant in x, but it's the phase space density. I should have called it, maybe I should have called it f, which is what I've been calling it up till now. Alright, why don't we just quickly make the investment here. Oh, I see what happened. The whole damn thing moved. Alright, F, P, P, F, P, P. Alright, for F constant, it means that every place in phase space is filled equally. By Liouville's theorem, that's clearly a solution. So, and it's a steady state solution. So, if df/dp is 0, well, this is obeyed. So one way to get the way to get the relation between A and E is not to use n, but to use the phase space distribution. And in that case, and when you write it that way, it's always df dt equals, well, if it's isotropic, it's 1 over p squared dp, and this is the diffusion and momentum, dp P times F. So this, where F is, when F is space distribution, then this is always true. Now if I say that N is equal to F times some power of P,
No, I'm saying P squared.
what?
In equation 1, the P squared for the DFP.
Here. Right. Because the flux is, thank you. So if N is d FdP squared, that immediately gives me then I know N is proportional to P squared, is the steady state solution. And once I know that, then I know the relation between A and D. I pick A with respect to D such that the equipartition solution is always a steady state solution. So when I stick P squared into here, the right hand side should always be 0, and that fixes A relative to D. F P P okay. Now I think I'm just going to skip to the case where there is recoil. When there's recoil, then the relation between A and D changes, because if there's recoil, it means that a particle that's, if a light particle is very energetic, let's say the scatterers have finite mass, and let's say a particle has more energy than the scatterers on the average. Well, then we know on the average it's going to lose more energy by recoil than it will by receiving hits.
What is the
Reta. It means that it can also lose energy. It doesn't just scatter elastically, but it can impart some of its energy to the scatterer itself, if it has enough. So then we use the same principle. We just decide that A and D have to be such that if the scatterers have a finite temperature, then a steady state solution is when the light particles have the same temperature. So let's say we're talking about Compton recoil, photons being scattered by electrons. What's the final energy spectrum of the photons? Now if you say black body radiation, that's not really true, because for black body radiation you have to actually create photons. Black body radiation tells you there's a certain number of photons, and if you had less than that, they would get emitted. More would be emitted. With Comptonization, you're not assuming there's any photon emission mechanism. There's only scattering, so the total number of photons remains the same. And if you didn't have enough photons originally for black body radiation, then you won't have enough in the end either. But you will get what's called a gray body spectrum, which means it's the same shape as a black body, but it has less photons. And it's because the photons did everything they were supposed to do to achieve thermodynamic equilibrium with the scatterers. And the fact that there wasn't enough of them is not their fault. So, so let's say that the P and E refer to the momentum and energy of the heavy particles, and little p and little e refer to the momentum and energy of the light particles. But the light particles are photons here. So I'm just going to use energy and momentum. Okay. That's a cat.
Yeah, someone's killing it.
You sure about that?
Sounds like that. No, it's some video thing, I guess. No, it's outside.
I have no idea.
No.
Okay. So little p is the momentum of the photons, and let's assume they scatter by a large angle. So delta p is of order p. Delta big P is the amount of momentum that the electron picks up, scatter picks up, and therefore it's, well, by conservation momentum, it's the same as, I don't know why this is approximate here. This is, should be an equality sign. Why is this not sticking? M delta V is equal to delta P, delta little p, because with the photon loss, the heavy particle gained in terms of momentum. Okay, now, I see. I'm assuming the heavy particle was at rest, approximately, because that's where I'm calculating just the recoil. When it's moving, I'll get energization of the photons, but I want to separate the recoil and the smacking. So delta E, if the scatter had originally been at rest, is a half m delta V squared, and when I write this in terms of the original photon energy, since energy is conserved, I know that Well, you know what? I'm just gonna write sub gamma to refer to the photon energy, and this refers to the scattering energy. So the point is the rate of recoil is proportional to the square of the photon energy, because it's proportional to the square of delta p, because the scatterer was presumed to be non-relativistic. So the loss, the rate at which the photon loses energy, well, it looks like it's proportional to E squared, folks, and not E. I assume there should be another E here. Look, I could have just said that, I could have just called both these terms A and said that A had, was E minus. And I don't even know if it means photons or protons here. I should have taken up my notes. Well, it's after 4, so why don't we just stop here and then finish this tomorrow, and that'll be it. And we can discuss the final. You probably will. Who's taking the course for? Just a second.